next function we're going to go a bit more in depth on is a quadratic function. And we've talked about our basic quadratic functions are the x squared function, whose graph is a parabola. And so what we're going to do is we're going to look at transformations of the parabola specifically and how to calculate where the vertex, x-intercepts, y-intercepts, and other aspects of the parabola are. Okay? So the first thing I want to point out is that there are two different forms that we generally use to represent a quadratic function. Okay? The first one is what we call the vertex form. And it really comes from all the transformations that we've seen so far. Your vertical shift would be the k value, your horizontal shift would be the h value, and then the a gives you your vertical stretching or compressing, along with your vertical reflection or reflection across the x-axis. Okay? And so this form, I said, is called the vertex form. And it's the vertex form, it's called that because the coordinates of the vertex show up as the values of h and k respectively. Okay? And so what happens is, if you have the standard parabola, right, just the x squared function, the squaring function, if you take that function and shift it, notice the original vertex is at 0, 0. Vertex meaning either the minimum or if it opens down, it'd be the maximum. And so that vertex there, when you shift this graph by k units up or down and h units right or left, then that vertex will shift k units, h units, and end up at the point h comma k. All right? And so wherever the new parabola would be, that vertex would have coordinates of hk because you're adding k to the y value and h to the x value, and that would give you both shifts. Right, a horizontal shift of h and a vertical shift of k. All right, and that works whether it's positive or negative, wherever those are. Okay, so the vertex is always going to be the coordinates h comma k every time. Okay. There's also a very important feature of a parabola called the axis of symmetry. We saw that it has symmetry when we looked at it in the library of functions, and it will generally be the y-axis, that's the axis of symmetry for the original squaring function. But once you shift it horizontally, that axis of symmetry is going to move to the horizontal value, right? So it starts at 0 and moves over to h. Now if you shift the graph vertically, the axis of symmetry stays right where it is, right? The axis doesn't move if you shift vertically, only if you shift horizontally. Also, a reflection isn't going to change the horizontal, or I'm sorry, the axis of symmetry. So the axis of symmetry changes based upon the h value. And remember that we've learned recently that vertical lines have an equation of x equals a number, right? X equals a, we've said in the past. And so here with the axis of symmetry, it is going to be a vertical line, and it's going to run through that h value. So we'd say x equals h is always the vertical axis of symmetry. Okay? Okay, now there are some other very important points or features of a graph of the parabola. But before I get into those, the other form of a parabola or quadratic function that I have up here is called the standard form. It's what you would get if you took the vertex form and expanded it out into just a polynomial with individual terms. Right? If I were to take the x minus h, square it, expand that out, distribute the a through, and then add the k. This is the standard form, and it has some very important uses, and so we'll come back to that, but I'm going to save that for another video. Okay, so I'm going to come back to the standard form. Okay, so anyway, the y-intercept of these graphs, and there will always be a y-intercept on a parabola because the tails extend indefinitely. So no matter where it gets shifted to, they're always eventually going to hit the y-axis. So the y-intercept is always going to be found simply by plugging a 0 in for the x value. It's f of 0. Right? So if I were to evaluate this, think about how that would work out. That'd be a times 0 minus h squared plus k. Well, a negative h squared is the same as h squared. So this would be a h squared plus k. And whatever you get when you calculate that is going to be your y-intercept. Okay? Usually we would just call that 0 comma f of 0 and not worry about remembering a formula because it's not too hard to just plug a 0 in and calculate it. It might actually be harder to remember the formula, but it's up to you, I guess. Okay, so that's a y-intercept. Now the x-intercepts are a little bit more interesting. Remember, for an x-intercept, that's what you get when you plug 0 in for the function value. And not all parabolas will have x-intercepts, right? This one that I drew over up and to the right, that doesn't have any because it starts above the x-axis and goes up from there. Here I have a graph that only has one x-intercept. And so if you have that shifted just horizontally but not vertically, you'll only have one. It's also possible to have graphs that have two x-intercepts. Okay, so that's an option. And of course, if you flip the graph and reflect it upside down, you can have the same situation where it's below the x-axis and never hits an x-intercept, or where it's right on the x-axis and has one, or where it's above, and when it opens down, you're going to cross it twice. Okay, so you could have 0, 1, or 2 x-intercepts for a parabola. Those x-intercepts, again, are found by setting the function equal to 0, and you're going to solve for x. Okay. Now, there's not a nice formula for this. You just have to solve it. However, there are times where you're going to have to take a square root at some point, right, to get rid of the square. After you subtract the k and divide by a, then you have to take the square root. If the number on the other side is positive, then you can take the square root and be just fine. And you'll end up with two values, a positive and a negative. Okay, and that's where you get a situation like this. If you end up with a 0 after you've subtracted the k and divided the a, if you end up with a 0 over here, then that means you're only going to have one answer, one x-intercept, because when you take the square root of 0, you just get 0. There's no plus or minus there. If, however, after you subtract the k and divide by a, if the other side is negative, then when you take the square root, you get a complex number, which we can't graph, right? Complex numbers are not something we can put on here. They don't show up on the real number line. And so we would not have any x-intercepts. And so if you have a negative over here, then you would have a situation where either the graph is opening up completely above the x-axis or down completely below. All right. Okay, so those are some situations that you could have, but there are 3 possible situations for an x-intercept. There is also another very important point on a parabola, and I'm going to call it the point symmetric to the x-axis. I'm sorry, I just said that wrong. It's the point symmetric to the y-intercept. I don't know where x-axis came from. And so, get rid of a couple things here. If I were to sketch a graph to illustrate this better, let's say I have a parabola. I'm going to look for the point symmetric to the y-intercept. Okay, point symmetric to the y-intercept. Then we know the y-intercept here is 0 comma f of 0, right? You plug in a 0, you get out f of 0, whatever that is when you calculate it. Well, what happens is you have your vertical axis of symmetry, and that's always h units over, right? So to get over to that axis of symmetry, you have to go over to h, or back to h, whatever h is, wherever h, left or right, doesn't matter. Well, to be symmetric, you would have to go another h units over to get to the point that's symmetric, right? Symmetry means it's equal distance on either side. And so the x coordinate of that point wouldn't be h, it would be 2h, right? H plus h, it would be two of them. And so the x coordinate for the point symmetric is going to be 2h. And the y coordinate, well, it's going to be at the same height, right? The symmetry means it doesn't move, vertically it doesn't change, same height. So the y value would be the same. It's going to be 2h comma f of 0. Right? So you can always find the point symmetric to the y-intercept. That way you can, if you're plotting the graph, you can get a pretty accurate idea of how wide the graph will open, and you can get the symmetry in there as well. So you don't end up with one side being really wide and the other side being really narrow. It would allow you to get the proper symmetry to your graph.